Good evening, ladies and gentlemen. It's a pleasure for me to welcome you all in today's special lecture, which is part of our workshop. Happy Republic Day to all of you. And I'm Dipankar Banerjee from Aryabhatta Research Institute of Observational Sciences, and I'm the co-investigator of this workshop and currently the director of the Aryabhatta Institute. It's a really privilege and honor for me to introduce to you today's speaker, Shri Kiran Kumar. And we're going to have this special lecture on ISRO exploration missions from him. So I will take this opportunity to very briefly introduce him to this audience. Shri Kiran Kumar is Vikram Sarabhai Professor at ISRO Bangalore and member of the Space Commission, Government of India. He's also member, Governing Council, Indian Institute of Science, Bangalore. During 2015 to 18, he has served as Secretary, Department of Space and Chairman, Indian Space Research Organization. Shri Kiran Kumar was born on October 22, 1952 in Hassan, Karnataka. Holds an MSc degree in Physics, Electronics from Bangalore University, and MTech degree in Physical Engineering from Indian Institute of Science, Bangalore. He has steered the implementation of the applications-oriented Indian space program, which has facilitated rapid development of the country in many important spheres of Earth observation, communication, navigation, meteorology, and space science, as well as the development of the indigenous launch vehicles and related technologies for providing assured access to space. He has led design and development of more than 50 electro-optical imaging sensors flown on various spaceborne platforms, starting from Bhaskara in 1979. Further, his role in the success of Chandrayaan-3 Mission and Mars Orbiter Mission has been significant. He has co-authored 85 publications in various national and international scientific journals, conferences, and symposiums. In recognition of his contributions, he was conferred with Padma Shri by the President of India in 2014. Normally, just before the Republic Day, we have this special announcement as it happened yesterday evening. Other notable honors conferred on him include Rajyostava Award in 2015, Shri M. Visvesvaraya Senior Scientist State Award, for 2013 by Government of Karnataka, Lifetime Achievement Award from Karnataka Science and Technology Akademi in 2016, IISc Distinguished Alumnus Award for 2015, Gujarat Ratna Life for Innovation Award conferred by Gujarat Innovation Society in 2014, Lifetime Achievement Award by Andhra Pradesh Academy of Sciences in 2016, Bharat Ratna Sri M Visvesvaraya Centenary Award by University of Mysore in 2016, GM Modi Science Award in 2016, HK Firodia Vigyan Ratna Award in 2017, Santokbaa Award instituted by SRKKF Surat in 2018, and ISRO Lifetime Achievement Award 2018. He has been conferred with the prestigious 2018 International Von Karman Wings Award instituted by the Aerospace Historical Society, together with the Graduate Aerospace Laboratories at the California Institute of Technology in 2018, and the Chevalier de Lucien Ballou Honor Award, the highest civilian honor by the government of France in 2019. We are really honored to have you, sir, in our platform and part of this workshop special lecture. Over to you, sir, for your lecture.
Thank you very much. Thank you, Dipankar. And it is indeed a great privilege to be part of this space radiation workshop organized between India and US. So I'll just share my screen. Give me a couple of seconds. Just 1 second. Okay. You are seeing the screen, I suppose?
Yes, sir. Absolutely.
Okay. So thank you very much again. And in fact, let me welcome on behalf of the organizers for this program and giving me an opportunity to showcase to you the activities that are being done at ISRO in terms of space exploration missions. So what I intend to do is I intend to take you through the initial developments and the various programs we have done for the space missions and where we are heading. So I'd like to just take you through that journey. And probably you're quite familiar that ISRO started its space program with the visionary approach of Dr. Vikram Sarabhai, who in the early 60s had made use of his friendship with American, Russian, French, and German scientists and brought sounding rockets in the form of kits and got them assembled and launched it at this Santokbaa Equatorial Rocket Launching Site, where these sounding rockets were used for conducting upper atmospheric research. And right from that time onwards, India and ISRO has been trying to make use of all the opportunities available to conduct specific space science experiments. And in Aryabhatta, which was launched in 1975, or our own SLV launch, Stretch Rohini series satellite in 94, or the Indian X-ray astronomy experiment and solar X-ray spectrometer in 2003, and a couple of dedicated missions. What we had, Chandrayaan-1 Mars orbiter mission in 2013, AstroSat in 2015, Chandrayaan-2, and currently, of course, the missions on Chandrayaan-3, Aditya, and XPOSat are all in the line. And beyond that, of course, Venus mission and some more are in the planning stages. We'll touch upon some of these missions in my subsequent slides. So this is how the whole activity started. The first launch took place with in the dilapidated church here, the sounding rockets getting assembled. And at that time, we really had very little resources. And no matter what it was, the activity of space science commenced with that. And gradually, we built up the capability. And Aryabhatta itself, while it was an opportunity satellite which Russians had offered to launch, the scientists, space scientists like Professor U.R. Rao, Kasturirangan, and they had built an X-ray, astronomy and aeronomy payloads, and also some solar physics experiments were conducted in this Aryabhatta. Then, as part of the Space Lab experiments, Anuradha was planned, and in this cosmic ray experiment was planned. And then this was a joint venture between Physical Research Laboratory, ISRO, and Tata Institute of Fundamental Research. And this provided direct measurement of ionization states of nitrogen, oxygen, and neon series. And then as part of our Stretch Rohini series satellite, which was again an opportunity satellite launched on our initial developmental launch vehicles, a gamma ray burst experiment developed at ISRO was launched. And it did, of course, pick up a couple of gamma ray bursts in the instruments flown on this satellite. And also a retarding potential analyzer developed by National Physical Laboratory was flown on this. And the activity, the data collected from this resulted in about 24 publications. And we were also able to do some ionospheric measurement parameter to study latitudinal variation of ionization structure, irregularities of plasma bubbles, etc. Then the X-ray astronomy experiment, which was done in 1996, of course, this was flown on our Polar Satellite Launch Vehicle, PSLV. And there were 3 identical pointed mode proportional counters, an X-ray monitor, which was developed by the KFR in collaboration with ISRO. And the orbit itself was viewing in a high background orbit. 2 to 3 months of observation in a year was what was possible. And it studied 20 X-ray sources, including a neutron star and black hole binaries. And this data again resulted in about 31 publications and helped 4 of the doctoral studies to be conducted. This success, of course, led to detailed discussion on our astronomy satellite, AstroSat. We will see later how the astronomy satellite, or AstroSat, has made significant impacts. Then similarly, on our geostationary platform, GSAT, we had a solar X-ray spectrometer called SOX, and this carried a high spectral and temporal resolution X-ray spectrometer. And this studied the disk integrated flux in the 4 keV to 10 MeV range. And here again, the instruments were developed in collaboration between PRL, Physical Research Laboratory, ISRO Satellite Center, and Tata Institute of Fundamental Research. This again was able to contribute to 10 publications and an RT2 experiment on board Russian Korona's Photon satellite again in 2009. And this was carrying low energy gamma ray X-ray spectrometer operating in the range of 15 keV to 150 keV and contributed to about 12 publications. So beyond this, of course, we went into dedicated space science missions, space science and exploration missions. And of course, the first was the Chandrayaan-1, which was again a very significant development for ISRO, because it was Chandrayaan-1, which was a large international collaboration satellite developed with almost 6 payloads from 5 countries. And using these payloads, Chandrayaan-1 made a huge impact, and it had also 5 instruments of our own. And using this, it also carried a moon impact probe, which actually touched down on the surface of the moon. And the major discovery of Chandrayaan-1 itself, we're all quite aware that it changed the perception of moon in a significant manner. Before Chandrayaan-1, moon was considered dry, probably presence of water, but the instruments carried by Chandrayaan-1, which was actually APL and NASA payloads, resulted in identifying presence of OH and water molecules, and then geologically very inactive moon was actually considered later as a dynamic and more volcanically active. Complete absorption of the impinging solar wind protons by lunar regolith, and almost 20% of solar wind protons are reflected. We'll see some results subsequently. And earlier, this magma ocean, there was not significant evidence, but then Chandrayaan-1 data, it was confirmed that global magma ocean hypothesis came out of this. And then lunar surface vulnerable to impacts of meteorites and other bodies, as well as energetic particles and radiations, making human settlement difficult. Detection of potential sites like buried lava tubes. And these were some of the significant findings of Chandrayaan-1. And then it has resulted in more than 150 scientific publications. And like we talked about, water molecules in lunar exosphere and also subsurface deposits, presence of large expanses of crystalline feldspar, then mini magnetosphere on moon, many craters, which we were able to do the three-dimensional conceptualization of that, volcanic vent, and rails connected subsurfacially. So these were some of the findings, mini magnetosphere, which came out on the geophysical research letters. And then protons reflected from magnetic anomaly regions were picked up, and then this study was carried out by Bharadwaj and team. And then first observations of proton entry into the near lunar plasma for magnetic field aligned flow. This was again an important finding which came out in geophysical research letters. And then discovery of new population of suprathermal protons around the moon. This again in geophysical research, it came out. Then transport into the near lunar wake or the right on the night side. This was all picked up using the Chandrayaan-1 data, and SARA instrument was flown on Chandrayaan-1, as you are aware. And then current view of the moon, the various activities. These were the work carried out by PRL and Bharadwaj and team, along with his colleagues in various international institutions. Then again, one of the important activities that happened, which got reported in geophysical letters, is the source composition of the ionosphere on the moon, and also electron density and photon transport. This was again radio occultation observations. And of course, as far as the overall impact of this was concerned, we had more than 180 publications, and the instruments that were flown on this, ISRO worked on that and improved on the instrument, and we will see in our subsequent Chandrayaan-2 results some of the things coming up as a result of the improvement that have happened on Chandrayaan-1 mission. Then this, of course, was an example of non-collapsed portion of a site which could be potentially site for future habitats, and also the evidence of recent volcanism on the Tycho crater, a 3D image of that generated from this, and solar wind surface interactions which were pointed out by SARA-based studies. And apart from Chandrayaan-1, of course, we had another mini satellite mission called YouthSat, where between USSR and India, collaborative work was done, and solar radiation monitor and radio beacon ionosphere and tomography instruments and limb viewing hyperspectral imager they were flown on this mission, and some of the results got actually published. And the tomogram reveals presence of ionization crests in Bangalore and south of Trivandrum between 150 to 300 kilometer altitudes. Then another very significant mission for us was Mars Orbiter mission, which again has made a significant impact in terms of its ability to do planetary mission and conduct such mission with the kind of launch vehicle that we had, very limited resources that was there. But then using this, while initially the mission was expected to stay for about 6 months, now we have already completed 7 months, and very soon some interesting newer type of experiments is under planning. And this mission itself produced more than 30 publications and data being made available through our ISRO satellite Space Science Data Center, and more than 7,000 global users from 50 countries have picked up the data of this. And it was also able to pick up the demos. And of course, this is just an image of the satellite during the RF testing process. And some of the results from this, which was very interesting, it carried a mass spectrometer, and using this mass spectrometer, it observed suprathermal argon in the Mars exosphere. And this was an important clue to understand the energy budget of the exosphere of Mars. And then it was also a clue to understand the escape of atmosphere from Mars. And there was also suprathermal atom, this presence, which was picked up to 500 kilometers using MENCAR, the mass spectrometer data. And these are just, of course, some of the images taken from Mars color camera. And of course, a view of an impact crater. Then, of course, a view of wind streaks, which was observed using one of the images. And then three-dimensional view of the Marinus from the MCC images. And of course, it also carried a 1.65 nanometer, very narrow band imager, and using that, the entire Mars sphere has been mapped, and these are some results from that. And then recently, of course, result came out that during the solar conjunction, by measuring the radio signal coming from the MOM, the observations which were carried out during the solar conjunction in June of 2015, data was generated, and using this, radio occultation experiments were done, and these results were actually published. And it also shows the temporal spectra frequency fluctuations in the 4 to 20 radii of the sun, and then earlier to that in a closer radii, how the things have been picked up. And these results are very much in consonance with the other findings. And solar coronal turbulence near maximum phase of solar cycle 24. This was one of the observations that happened. And you can see that one data set has come in the recent solar minimum. Then, of course, another very important mission where we were able to do a significant contribution to the observatory is an AstroSat mission. And here again, the activity was actually in collaboration with a large number of Indian institutions of Tata Institute of Fundamental Research, Indian Institute of Astrophysics, Inter-University Center for Astronomy and Astrophysics, Raman Research Institute, and all of them together were able to put a multi-wavelength telescope of ultraviolet, visible, soft and hard X-rays, and carrying these multi-wavelength telescope system on this satellite has made a significant observation and has provided very useful data for a large number of Indian researchers, and already more than 200 odd publications have taken place and 1400 plus users from 49 countries. And India is also able to provide this satellite as an observatory, and 11th announcement of opportunity cycle is currently in progress, and 30 data utilization projects have been handled using this. And one of the very important observations, of course, was the ability to look at in the far ultraviolet region, from the AUD FS01 location, where redshift range from 0.4 to 2.5 was picked up by this far UV telescope. And this telescope actually carried a completely indigenous payload with a far ultraviolet telescope realized within the country. And the sensitivity of this particular imager is extremely good, and that was the reason why these observations could be made, and it has made a huge impact globally on the data obtained from AstroSat. In fact, AstroSat also happens to be the first dedicated observatory which India has put into orbit. And results from AstroSat, another thing is a 7th thermonuclear burst with 65 kiloseconds of observations, which is done, and with a gap of 5.5 minutes. And also far UV observations of the butterfly nebula of NGC 6302. This was again another interesting observations from AstroSat. And another very interesting result that came out is the CZT imager. This is mercury cadmium telluride imager, which post-launch, actually the research team were able to do a lot of innovative analysis and bring out that X-ray polarization measurements of crab pulsar could be identified, and phase resolved X-ray polarization measurements they could showcase. And this was another very interesting result which came out of AstroSat activity. And then the very high resolution of the UV telescope became apparent when compared with the GALAX data, and also the AstroSat pointings which have been done. This image shows what all regions have been covered in the sky. And then gamma ray burst observations from CZTI, also more than 463 odd detections which have happened using AstroSat is showcased in this particular image. Then, of course, came the Chandrayaan-2, and in Chandrayaan-2, the important thing was all the instrument that was carried on Chandrayaan-2 was totally within the country, and we had a number of institutions supported by ISRO working on these imaging payloads, and also both the imaging instrument, which is a hyperspectral imager, which we extend the wavelength region from 3 microns up to 5 microns. And then, unlike the mini-SAR or a single frequency synthetic aperture radar in Chandrayaan-1, in Chandrayaan-2, we had a 2 frequency, dual frequency synthetic aperture radar, L and S. And both of these have been able to provide very interesting observations. And already we have more than 2 years of data have been collected, and using the hyperspectral imager in the infrared region, the entire moon surface is covered. Few of the gap regions are being now planned, and it will be covered in very soon. And already more than 24 publications have occurred, and data sets have been released to the public, and currently 75 proposals are under data utilization announcement of opportunity. And this image, Chandrayaan-2, is going to provide us ability on surface mineralogy, elemental analysis, surface topography, neutral exosphere, ionosphere, and lunar water ice. And the three distinct areas is the water on the moon, surface water using IIRS, subsurface using dual band SAR, L and S band, and also exospheric water using CHASE mass spectrometer. Then lunar composition, again using IIRS, and then class plus X-ray monitor and dual frequency SAR and ionospheric studies using DFRS. Then lunar topography using global mapping of TMC2, and also a very high resolution imaging capability, which is there in the very high resolution imaging instrument OHRC on this. And the dual frequency SAR, which is an L and S band SAR operating, actually has made a very significant observation capability addition to what is being picked up on moon. And this actually is a very compact payload with a data rate of almost 160 megabits, and it's capable of providing 2-meter resolution imaging. And it's already covered quite a bit of regions of the polar regions, and some interesting observations which are there, which shows subsurface impact melts, and also the Tycho crater, and decomposition of the images corresponding to this crater region, showing both crater ejecta melts and also the central peak. These observations have been done, and a lot of work is currently in progress using this data. And then again, water ice bearing region in using fully polarimetric DFSAR data. This is one of the work that's going on. And then regions bearing water ice in blue and cyan color is showcased in this image. A lot of work by the scientists both at within ISRO and outside ISRO are working on these data sets to bring out results. Then if you see some subsurface features also being picked up using the data, and a lot of modeling work and also determining the dielectric properties of the regolith and subsurface, and using them as inputs for correcting the data. All this work is going on. And these are some very high resolution images taken from OHRC, just to give an idea of the kind of images that are picked up using this instrument. And then, of course, Sarabhai crater, which was imaged by, and the interest in this was, of course, last year happened to be the birth centenary of Dr. Vikram Sarabhai, whom we consider the father of Indian space program. And this was just a crater image picked up using the terrain mapping camera and showcased. And then, of course, imaging spectrometer, which I was trying to explain, is one of the very key developments carried on Chandrayaan-2. And already a lot of data collection has happened, and work has shown very significant improvement in many of the details about our understanding the origin of lunar water. Towards this, some data. Then does the water vary with the temperature? Is water concentrated in geologic locations? Many of them efforts are on. And then determining the form, abundance, and distribution of both water and OH across the targeted area in both sunlit portions, and the variability in latitude and longitude is also one of the work that is done. And this gives us a 80-meter spatial resolution. And since you are able to go up to 5 micron, the capability of this instrument has been effectively utilized for bringing out many new results, and more results are expected to come out of this capability. This again showcases the lunar radiance distribution as observed. Then in the Copernicus crater, again, some of the things that have been found, that relative hydration strength And then you can see, particularly in the 3 to 5 micron region, how the band shapes and band depth and are changing, and the data is actually providing a very valuable inputs for the research community. And then unambiguous detection of this, and also because you are able to go from 2.7 to 3.1 micron, and even the small shifts in the peak and depth are being utilized for making analysis of the data using this. And the entire lunar surface thermal map using high resolution imaging spectrometer is being carried out right now. And even the class instrument, also the X-ray fluorescence, has provided extremely good inputs, and you have been able to make studies using flares and flare time, and a lot of significant work is in progress using this data sets. And again, Argon 40, this is again another important addition to the understanding. First global observations of the lunar surface with respect to mid-latitude variation and low-latitude observations have been possible using this. And actually this showcases the distribution of this argon distribution on the lunar surface. This is indicative of both unknown or additional loss processes, and then moonquake regions, etc. Then solar X-ray XSM actually is another very important instrument, and again sensitivity of this is extremely good, and it's able to study on make observations not only during the quiet sun period, and it has also made a lot of significant inputs to the understanding of the micro flares, and then also the photospheric contributions of whether it is magnesium, aluminum, silicon, etc. So these are being attempted using this data, and robust measurement and evolution of abundances even during small flares have been picked up using this. Then again, of course, magnesium abundance and OHRC data is also used for identifying the mini crater or the small crater distributions, and through that the age of the craters. Then again, this is just an example of the elongated asymmetric crater impact studies which have been carried out. And then hydration maps, which I already pointed out. And because of the total water concentration varying between the near 0 to 800 ppm have been picked up using this data analysis. Now, of course, beyond Chandrayaan-2, Chandrayaan-2 itself has already completed more than 2 years now, and then we have enough fuel and the satellite is functioning very well, and it's expected to carry on for many more years. And all the first completing the complete mission analysis with respect to IARS has been completed, and now more detailed studies using the SAR and other instruments, the emphasis will be there. And also in future, there will be attempts to reposition the satellite to go to lower orbit and collect some more data post Chandrayaan-3, because Chandrayaan-2 is also going to provide as a backup relay system for Chandrayaan-2. And in Chandrayaan-3, now the unsuccessful attempt of lander is being taken care of, and we have a Chandrayaan-3 mission, which is the follow-on for Chandrayaan-2, and it carries a lander and rover and lander carried on a propulsion module. And then this propulsion module sometime this year is the expected launch of this. And then the payloads on lander are the Langmuir probe, then Chandra Surface Thermophysical Experiment, instrument for seismic lunar activity, and then alpha particle X-ray spectrometer, and laser-induced breakdown spectrometer. These are the instruments, and these have already been integrated with the rover instrument, and things are getting ready for launch and test later this year. And subsurface chastity experiment is planned in this, and this is the first instrument which could look at surface and subsurface measurements of temperature using this instrument. Of course, beyond Chandrayaan-3, currently this year another mission that is expected is the Aditya L1 mission, where the satellite is nearing the final stages of testing, and tests are in progress. And this satellite will be put in the L1 halo orbit, and coronal studies, hard X-rays, soft X-rays, UV imaging, and then the charged particle studies, magnetic field, all these experiments are going to be carried on this mission. And uniqueness of this mission itself is CME dynamics close to the disk, between 1.05 radii of sun and beyond, coronal magnetic field and topology, then flare observations, and onboard intelligence to detect CMEs and flares for optimized observation. Solar wind electrons, protons will be one of the measure parameters. Then specific identified flags and count information through telemetry for early information on space weather events. Those are some of the plans that are there. And this just gives you an indication of the type of spacecraft that is getting ready. And the instruments themselves are the visible emission line coronagraph, then SU-80 and the solar ultraviolet imaging telescope, then the low energy X-ray spectrometer, then high energy spectrometer, then solar wind experiment instrument aspect, and then plasma analyzer package for Aditya called PAPA, and advanced triaxial high resolution magnetometer. So these are just some images of the payloads that are getting ready for the final tests and transportation to spacecraft. And these are some images of these payloads. And this, of course, the flight models of the aspects unit and the PAPA unit. And apart from this, again, of course, we have the XPOSat or the X-ray polarimeter satellite, which is also getting ready for a launch. And this is a dedicated satellite for polarization measurement in X-ray. And then polarimetry is an important diagnostic tool of emission processes. And there are two payloads here. One is a polarimeter instrument, and the another is an X-ray spectrometer. And a deployed view of the XPOSat is shown here. And then, of course, there is another mission which is in the final stages of approval and then final discussions. DISHA, called the Disturbed and Quiet Time Ionosphere Thermosphere System at very high latitudes, high altitudes. And then it carries neutral mass spectrometer, air glow photometer, drift meters, auroral X-ray imaging spectrometer, then high frequency Langmuir probe, upper atmospheric visible air glow spectrometer, and the like. And these are the things that are planned. And this, along with Aditya, it is also expected to provide some interesting observations. And ISRO is also working with JAXA for a possible collaborative mission with JAXA. This is, of course, phase A study is in progress. And then based on the collaborative efforts, it's possible that this will be a 6 months mission life mission where ISRO, JAXA are working together, and possibly NASA is also working along with JAXA in this. And as the collaborative mission progresses, this expected to happen in a couple of years from now. And if you look at on the whole, the overall exclusive space science mission activities, then you're starting from Chandrayaan-1 in 2008, then the Mars Orbiter mission in 13, and AstroSat in 2015, then Chandrayaan-2 2019. Now this year we expect to add 3 more, the Chandrayaan-3, then XPOSat, Aditya mission, and then the 2 more missions, Disha H and L, and then Venus mission is still in the final stages of project formulation and approval stages, but then these are the possible future missions which ISRO is looking at. So with this, what I intended to talk to you about, covering the gamut of missions that ISRO has done during the course of its journey, starting in the early 60s and till now, where we have gone and where we have moved. And in the process, collaborating with other space agency wherever it's possible, and doing indigenous development of the technology, and also showcasing some new way and innovative way of bringing in some of the observations and providing to the Indian scientific and community our own observatory, etc. has all been attempted, and we have had some success and reasonable progress, I would feel, with it, considering the kind of resources that have been made available to the space program. This is what has happened, and in future the scenario is changing quite rapidly in the country. The country is trying to look at how space technology itself can be actually becoming more and more operative from the even the private domain. Probably some of you are aware, earlier there were teams, private teams, who are trying to do moon mission independently, but in future we will see many Indian entrepreneurs getting into space science missions also. So with this, I complete what I intended to talk to you about. I'm available for any questions that you may have, which I will try and answer to the best of my ability. Thank you very much for the patient hearing.
Thank you very much, sir. It has been a wonderful journey and an apt, space exploration in a special day of Republic Day. We are all proud of our achievements and the indigenous development within the country. I think you have aptly showcased today. So with your permission, sir, I will take a few questions which are there in the chat box. Actually, there are 75 odd discussions going on in the chat box. There are lots of interest among particularly the students about different student program in ISRO. It shows clearly how enthusiastic the younger generation is, to work with ISRO, and they're always looking for opportunities. And I'm happy, actually, quite a few people have also answered in the chat box. I will share with you that also about the opportunities that are there on ISRO website. So let me just take a few questions from the chat box for you. Are there any astrobiologists working in ISRO now with respect to effect of space radiation on life in space? Does ISRO have any plan of astrochemistry or astrobiology program in future with work for chemists and biologists too in ISRO?
Okay. See, probably we are all quite clear that ISRO has also started its human space program. And as part of this human space program, there will be also a number of opportunities where some of the unmanned missions which we are going to do even prior to the actually manned mission, in that a lot of space science experiment opportunities exist. And we do have the groups working, not within ISRO. ISRO itself does not have any astrobiologists working, but actually ISRO is supporting the astrobiology related activities, and probably sometime early even we carried an instrument into the upper atmosphere and then picked up some cryostats, and using cryostats some samples were picked up. But anyway, coming to the current, there is a lot of interest for future astrobiology and astrochemistry related activities. And today, the mission, both space science team as well as the human space science mission teams are trying to work with the Indian academic community, both in biology as well as life sciences, to work in this area. And there will be definitely opportunities for the researchers and students in the country to collaborate with ISRO in this in the near future.
So with your permission, I would like to just comment. In fact, this workshop which we are conducting, tomorrow's day is called actually Radiation and Biology Day. And we have actually quite a few, biologists, astrobiologists also. They're going to talk about this. So these are very early, as you indicated, in the academic domain also. There are some early programs and there are initial results, and we would really love to work with ISRO on this avenue as well. So let me take the next question. Sir, when we expect Indian spacewalk?
Okay. Yeah, see, right now, as probably you're aware, that the government had tasked ISRO to do before the 75th anniversary of the independence, to carry Gaganauts into space and bring them back safely. But because of COVID and the related slowdown and also the economic situation, this program got slightly delayed, but the work is in progress, and these are the subsequent steps. First step is, of course, carrying Gaganauts into the space and bringing them back safely. And after that, getting into both space station and continuing the space program. And this, as the country's economic strength increases and more resources become available for these activities, the spacewalk from the Indian Gaganauts can be expected sometime in future, but not in immediate future. It's a process by which, through the government, as it becomes economically stronger and its priorities allow more resources to be made available, and as the private enterprise also moves ahead in this. You can also see today, the India is trying to promote enterprise to get into the fourth frontier of space, whether it is space tourism or otherwise. So in these areas, how things will progress and come out is actually we have to wait and see. But the government's program itself of spacewalk will be not in the immediate future. It will be taking some years.
Thank you. The next question is, what are the new news about movement on Mars surface from this Indian mission? Do we have any new findings?
Probably I'll have to refer it to some of our other colleagues later. But right now, I do not have any specific answer to that question.
Yeah. So there were a lot of questions about the data availability of these missions and so on. And I think in the chat box, I could also notice that people have pointed out to some of these things. For example, AstroSat, data is hosted at IUCAA with jointly with ISSDC, and somebody has put the website and the link as well. So would you like to comment a little more on any of the data availability?
Correct. Yeah, see, it has been the effort of ISRO to make this data of all the space science related activity available. And currently, like you said, as far as AstroSat data is concerned, it's available at IUCAA as well as ISSDC. But ISSDC hosts a lot of other data also, Mars mission, Chandrayaan-2, Chandrayaan-1, and in fact, Chandrayaan-1 data, some of the student community have conducted their doctoral research using the data hosted by ISSDC. So, but still, I think our efforts to make it known, we need to work on that. In fact, programs like whatever this workshop, we will need to identify specific small activities where the availability of this data can be showcased in some way. And then we would ask our space science team to conduct maybe specific activities in workshops of this kind in future and make this more and more known. Otherwise, definitely the outreach attempt is in progress, but obviously the question shows that we have not been very successful in reaching out to all the people.
Yes, sir. And I would like to take this opportunity to also mention that for Aditya L1, AD's Aryabhatta Institute has been granted this, site support cell, center, and that will be again our efforts will be to, train these younger students with the utilization of the Aditya's data and also sharing the data and so on and so forth as and when they are available in the domain. So thank you very much, sir. There are lots of questions in terms of, as I mentioned, the students in terms of their career opportunities. So would you like to say, very briefly about, undergraduate, postgraduate or PhD programs, if you have some comments?
Yeah, with respect to the career opportunities also, see, within ISRO itself, the opportunities are of course very limited, but today the way the things are picking up in academic institutions and then more and more data being made available through various programs, there is going to be a significant opportunity in the various academic institutions and in the research community. But within the organization itself, the number of openings will be very limited. It will be few in a year, that kind of thing. And you also are aware that we have Indian Institute of Space Science and Technology, where again, a lot of R&D activities goes on in that. And even the students coming out of that research group are also will be vying for the opportunities available within the organization. But what is expected is in the country, there'll be a lot more opportunities because this area is now becoming both even outside the government also a significant progress is happening.
Thank you. Thank you very much, sir. Now I will take this opportunity to request Dr. Madhulika Gothakurta from NASA, who is the PI of this workshop, to do the vote of thanks, please.
This was actually an extraordinary journey from a space organization being dedicated to bettering human life on Earth to opening it up, to exploration of science in the cosmos. Thank you very much for this presentation. And as I look at the chat, there are about 150, I think, student participants that you have stimulated in terms of training the next generation. And I think as you were talking about outreach, these are the ways. I think if COVID has given us anything, it has given us the gift of being able to allow a diverse group of people in a way we couldn't do before. I personally myself was going to join either ISRO or TIFR, but left the country in 1980, right? And since 2003, I have worked with colleagues at ISRO and academic institutions to forge collaboration, did the first International Living with a Star workshop in Goa in 2006, followed by 2016, and you can see the result. There is a vibrant community with missions. And what I'm seeing, this workshop as a nexus is bringing all of this together. The list of missions you kind of portrayed, the future missions, the past missions, sun is very much at the center because it's providing the elements of interaction for physics and for biology in space and on Earth. I mean, it's really humbling for me to see that. And I feel proud as having been an Indian citizenship, I'm a world citizen. That's how I look at myself. I want to take the opportunity to thank from myself and on behalf of the organizing committee for your presence here. And I want to wish everyone a really happy Republic Day. And I want to put this word out that maybe we should take this opportunity also to capture the moment with a group picture, if that is possible. We are so far away, we just don't know what technology allows anymore. So I'm just throwing that out for Dipankar, who has graciously been the host from Aries.
Yeah, I would request actually all the participants to turn on their videos, please. Then we can take a group picture. Yeah, this will be a good time for the participants. If you have your cameras, you can turn on the cameras, and then we'll be taking a group picture with Shri Kiran Kumar. It will be a lifetime opportunity for all of us. Yeah, I will request my colleagues to take few screenshots to cover as many people we can, and then we can create a collage. Thank you very much. Thank you. Thanks a lot. Thanks a lot. Good night.
Namaste. Also wish all of them happy Republic Day. Thank you.
Thank you, sir. So we will meet tomorrow morning, the workshop participants. Of course, this was a public lecture, but we have 200 odd participants in the workshop, and we request you to join tomorrow morning Indian time.